So this is Topic 1, Lesson 4B podcast, and this podcast will be on the gas laws. Gas behavior is influenced by three main factors, and so during this podcast we'll be talking about those three main factors, as well as how those factors have a relationship with each other. That relationship will decide upon the gas laws, the three gas laws that we will be talking about in this podcast. And so let's talk about, or let's identify the three factors that influence gas behavior. One of them is volume, and that mainly is because out of the states of matter, gas is compressible. Liquids and solids are not compressible because their molecules are packed so tightly together. It's a good thing in terms of this is how brake lines work, that the fluid has to be completely filled, that brake line. Otherwise, when you compress that brake, you're not going to be getting what you want in terms of stopping your tires. If there's a leak in your brake line, you'll definitely be able to tell because gas will get in there and it's not going to work as well. So gas is compressible, and so volume does have an influence in how the gas behaves, as well as pressure and temperature. So these are the three main influences in terms of gas behavior. So when you're watching this podcast, you want to be keeping these questions in mind. Would it be a good idea to pack an unopened bag of potato chips in your checked-in luggage if the baggage area of your plane, where your luggage would be going, is not pressurized like the rest of the cabin of the plane? And could you explain why or why not? Why would you want to do that or why you wouldn't do that? And in your explanation of why, you should be able to prove it mathematically by the end of this podcast and by any other background knowledge that you have. So at this time, what I would like you to do is I'd like you to think about previous knowledge. I'd like you to think about what you know in terms of plane and pressurized, and thinking about the bag of potato chips and what you have seen happen to other things that are closed like a bag of potato chips, and try and see if you could answer that question and make a pretty good hypothesis. Number two, another question you should be thinking of is, why does a hot air balloon rise? Now, I'm not asking you to tell me, well, a hot air balloon rises because you put heat in it and heat up the air. Well, yes, but why is that heating up the air make the balloon rise? What is that relationship between the balloon going up and rising and this temperature? And what is the mechanism that's allowing it to happen? And lastly, how can I make a can explode or implode? And again, why? So if I can make a can explode, how do I do it, and why is what I'm doing to it make it explode? And then vice versa. What if I wanted to implode? How would I change? What would I change about that experiment? And therefore, what is the mechanism that allows something to explode or implode? So here is the first law that we're going to talk about in terms of gas behavior. And this is Boyle's law. And Boyle's law shows a relationship between volume and pressure. So we had three variables that affect gases, those being volume and pressure and temperature. In this case, I'm just showing a relationship between pressure and volume. So temperature has to be constant in order for us to be talking about Boyle's law. If temperature isn't constant, and that's another variable in this, then we're talking about a different law, and that'll be explained at the end of the podcast. So with Boyle's law, let's just think about some practical applications to those, or what I think about in terms of Boyle's law. Well, since I'm a mom and I have young kids, I often think of cleaning up in their stuffed animal bin that they have. So if I have stuffed animals and I put pressure on them, or I squeeze them, increase the pressure, their volume goes down. The amount of space that they take up is a lot less when you're able to squeeze them. Therefore, I can put more stuff in their storage unit. But as pressure goes up, the volume goes down, and that just makes sense. Just think in terms of taking your hands and putting pressure and squeezing something, the amount of space that it's going to take up is less. And again, this is for gases because gases are compressible. With this relationship where one goes up and the other goes down, it's called an inverse relationship. And you can show an inverse relationship graphically. So let's just say as the pressure goes up, my volume is going to be going down, and it's a nonlinear relationship, so it's not a diagonal, it's actually a curve. So this is what it would look like if you were to, and we will be, doing Boyle's law, and at different pressures, seeing what the volume is, or at different volumes, seeing what the pressure is. And we'll graphically analyze that, and your graph should look as it does on the screen. With this mathematical equation, we can actually find out what a formula would be if you had pressure and volume at a certain amount and you changed one of those, how would the other change, seeing the relationship. And that formula is P1 V1 is equal to P2 V2, the one indicating the initial pressure and initial volume, and the 2 indicating the secondary pressure, or what the pressure changed to and what the volume changed to. So what I'm going to do right now is I'm going to read off to you a example Boyle's law problem, and I'll read the whole thing through, and then I'm going to read it as if I would reading it for the first time and writing down and getting ready to do my problem. Because remember, when you read science, it's not like reading English. You actually need to take the pieces and parts and analyze each piece and part before you get to the whole. So, all right, so let's go ahead and do an example problem. At constant temperature, what is the new volume of a 3-liter sample of gas if its pressure is changed from 0.5 atmospheres to 0.25 atmospheres? So let's go back through and chunk this up. At constant temperature, so my temperature is constant, so now I know I'm using Boyle's law. What is the new volume? So I'm going to say new is final, so that's a 2. So what is the new volume of a 3-liter sample? So a liter is a volume, so that must be my initial volume is 3 liters. Of oxygen gas, good, it's a gas, otherwise Boyle's law does not take an effect. And if the pressure is changed from 0.5 atmospheres to 0.25 atmospheres. Sorry, let me erase that a little. It looks a little not so good. Come on. There we go. So 0.25 atmospheres. So what I want you to do at this point is I want you to take these 4 variables. You know 3 out of the 4 variables that is in your mathematical equation, and I'd like you basically to just what we call plug and chug, plug those in, do the algebra, and come up with an answer. I want you to do that at this time, so you're going to want to pause the video, and then when you are done, you can unpause the video and I will go through the algebra and the correct answer. But please pause and do on your own at this time. Okay, so let's go ahead and go through and do the plug and chug here. So P1 is 0.5 ATM, and B1 is 3 liters. Boy, it doesn't like it when I want to go over it. So 3 liters. And P2 is 0.25 ATM. And V2 is what we're trying to find. So then when you do the algebra, you're going to do the 0.5 times 3 and find out that it's 1.5 is equal to 0.25 V2. And then you're going to divide by the 0.25 to get your V2 by itself. And if you do that, you come up with 6. And we can't have negative numbers, so I look up here and I see my initial volume is in liters, so my secondary volume will be in liters as well. Another thing you want to make sure of is that your other variables of the same unit, if one is in a different, they give you the initial pressure in atmospheres and the secondary pressure in some other unit of pressure, like let's say torr or kPa or millimeters of mercury, you need to make sure that you convert one of them to the other so that you're always having the same unit so that they actually will cross out when you're doing the algebra. And we'll talk about the different units for pressure here in just a minute, but before we do that, what I would like to do is I would like to give you a video or show you a video on Boyle's law and its application.
Here's what he's saying, guys. If I have a piston right here, okay, and I have a plunger right here.
Think of like a bike pump.
Like a bike pump. Yeah, bikes. I like bikes.
Actually.
Okay, and then if I do this in that plunger and I push it down harder, because I apply more force,
right.
The same gas down here and the same gas down here. This, of course, will have less volume, higher pressure.
Correct.
Okay, this is called Boyle's law. Okay, now, you know, Mr. Stams, this summer I had a kind of interesting experience. I rode my bike up a mountain.
As you do often.
As I do often,
yes.
I know. But while I was doing that, I conducted an experiment.
Oh.
So I think we should watch the Mr. Bergman Bike Up the Mountain video.
Okay.
And see how this applies to what we've been learning.
Okay.
Okay. Go. Here I am at the base of Mount Evans. Now, if you look back up here, you're going to see a bunch of mountains, and I'm about actually to climb that mountain here. But I have myself a bag of Pringles Minis, and I want you to notice the bag's kind of roughly like this, or you can push it down. It feels a little full probably compared to what you're probably used to if you live at sea level. But think of the gas particles striking this all of a sudden. But we're about to climb on our bicycles the highest paved road in America, which is the Mount Evans Road, and we're going to see what this bag looks like, and it's actually an application of Boyle's law. So we'll see you there in a few minutes, or hours. Rolling. And we're on the highest paved road in North America. Pikes Peak Highway riding up. Mr. Creekshauser, what altitude do you think we're at?
We're right around 12,000 feet.
12,000 feet. So, now look at my Pringles potato chip bag. Now, compared to what we saw, it's totally full. Boyle's law in action. How's that Boyle's law? Well, you see the gas inside, the pressure is the same. I'm breathing hard. The pressure is the same, but the external pressure at this high altitude is lower, and therefore the molecules, here I'll try and show this. Here, let's pause here. The molecules that are hitting this, well, there's fewer of them because we're at a higher altitude. But the molecules on the inside, the air molecules on the inside, they're the same number. Therefore, the bag expands. Now, we're going up there to the top of Mount Evans, 14,200 feet, I think. When we get there, I anticipate that this bag will be either fuller or possibly it will explode in my backpack from all the mess. Let's see it. I'm at the top of Mount Evans. It's a windy day, and I got my bag of Pringles Minis. Look at how big that is. Totally full. I think it looks, because of the Boyle's law, not very much air up here, even though it's windy, so it caused the potato chip bag to expand. You know what I ought to do? I should eat some.
So hopefully you understood that video of Mr. Bergman biking up that mountain to the highest road. And I'm not sure if you quite understand, so I want to go a little bit of a background information here. Where they are is near Denver, Colorado, and Denver is a mile-high city. So what happened is that bag of potato chips kind of looked full in the beginning, but at the end, it looked extremely full. Now, what happened is, let me try and show you here. This is where Bergman started. This is us, and this is where he ended. Now, because he's talking about pressure, let's just say here's our line for our atmosphere. We have a lot more pressure on us than Bergman did, and then he did at the end. So what ended up happening is down here, there is a whole bunch of dots, gas particles that are really close together. Here, they're a little further apart, and by the end, within that same space, about the same size circle, you count up the dots, there's a lot less on the top. And so what ended up happening is that when he got to the top, see, the inside of the bag didn't change in its volume of gases. It's a closed container, so it had the same number of gases that it did in the beginning. But at the beginning, all these dots would put pressure on the outside of the bag, pushing the bag in. But by the end, there wasn't as much on the outside pushing it in, so maybe there was more on the inside, and therefore, which there probably was, and therefore it's pushing out, and so the bag is expanding. Now, down here where we are, the bag would look like really crumpled in the beginning, and then it might look like this here, and by the end, it's completely full and pushed out to its sides. Here you can crumple, here you can kind of crumple, and here you can't crumple at all because it's completely expanded, showing that as pressure goes down, the volume goes up. Okay, so that's what that was supposed to be showing in that previous podcast, and I think, or that previous video on the podcast. So I'm hoping you were able to understand that, and we'll go over a little bit more when you get back into class. Now, as I said before, I also want to talk to you about the different units for pressure. And I'm going to do that by talking about, hold on. I'm going to do that by talking about STP. STP stands for standard temperature and standard pressure. So all of these different intensive properties that we've been talking about in the past, and constants that we will be talking about in the future, usually they have to deal with standard temperature and pressure under normal conditions. So what is standard temperature and pressure? Well, standard pressure, there's a few units that we'll be working with. ATM, and standard pressure is 1 atmosphere. That is the pressure at sea level. Now, we in Wisconsin here are at about sea level, so all of the calculations that we do and all the norms that we do, we are going to be under STP, or under standard pressure at least. We'll be under 1 atmosphere. You could also say, though, 760 torr or 760 millimeters of mercury. Meaning, remember we said that 0 degrees Celsius is also 273 Kelvin. They're equivalents. Well, that's the same thing here. So you can convert from one to another, because 1 atmosphere is 760 torr, is 760 millimeters of mercury, and is 101.3 kPa, kilopascals. So you will need to know these standard pressures, and as I said before, if the first pressure is in atmospheres and the second pressure they give you in kilopascals, you're just going to have to either convert the second one to atmospheres or the first one to kilopascals, so that they're both in the same unit. In terms of temperature, standard temperature is 0 degrees Celsius, which we know is 273 Kelvin. So you do need to know those. That's a 3. Really hard time making my 3s here. So it's 273 Kelvin. You do need to know these standard temperatures and pressures, because sometimes in these gas law equations you'll see it'll say, starting at standard temperature and pressure, it is changed to blah, 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 blah. Well, the students will say, well, they didn't give me enough numbers. Yeah, we did. We did it in words. If I tell you it's at STP, you know what temperature it's at, and you know what pressure it's at. So just keep that in mind. Okay, now back to our laws. The second law I'm going to talk about is Charles's law. And Charles's law is a relationship between volume, oops, get my ink here, volume and temperature. That's supposed to be a temp there. And the temperature must be in Kelvin. That is extremely important. Before you plug in any temperature amount into any equation in the gas laws, you need to make sure that you change the temperature to Kelvin, because we don't want to have any negatives. And Kelvin's the only one that doesn't have negatives, because absolute zero is 0 Kelvin, or negative 273 Celsius, or very negative Fahrenheit. So we don't want to deal with the negatives. That could definitely mess up our calculations. So we always make sure that our temperature is in Kelvin. Now, if you think about this, if you increase the temperature, remember temperature is an average kinetic energy, and kinetic energy is motion. So basically when you increase the temperature, you're increasing the motion of the particles. And if the particles are moving around faster, they're going to want to have more space. And so when the temperature goes up, the volume goes up as well. So because both are going up, or the reverse can happen as well, as temperature goes down, the volume goes down, this is called a direct relationship, because what one does, the other does as well. Direct relationship. And graphically, what does a direct relationship look like? Well, let's just say I put the temperature down here, and I put my volume over here. As the temperature goes up, the volume goes up, and that is a linear relationship. So temperature and volume graphically would look as it does on the screen. As with Boyle's law, we can also put this into a formula. And the formula for Charles' law is V1 T1 is equal to V2 over T2. And so now, again, what I'm going to do is I'm going to read an example problem. I'm going to make my list. I'm going to ask you to pause it, plug and chug, find the answer, then I will give you the answer afterwards. Okay, so here we go. First question. As the volume of a confined gas in 25 milliliters is 25 milliliters at 280 Kelvin, at what temperature would the gas be in 75 milliliters if the pressure is held constant? So remember last time we were working with a relationship between volume and pressure, and I said therefore the temperature has to remain constant. Here we're working with temperature and volume, so the pressure needs to maintain or be constant in order for you to use Charles' law. So let's break apart this question. It says the volume of a confined gas is 25 milliliters. Milliliters is the volume. 25 milliliters at 280 Kelvin. Well, great, it's already in Kelvin. Wonderful. At what temperature, so, oops, that should be T1. At what temperature, so T2 is what I'm trying to find, would the gas volume be, or what temperature would the gas be if the volume was changed to 75 milliliters? So here, this is where you would pause, you would go ahead and plug and chug, and come up with an answer, and then unpause and see if you are correct. Okay, so let's see if you are correct. So you would take 25 and you would divide it by your 280. It would be equal to your 75 divided by x. Now here you would cross multiply, so you would say 25x is equal to 280 times 75. And then once you do that, you would then divide both sides by 25, or you can do it right away and see that. So then x would be equal to 280 times 75 divided by 25, and you should get an answer of 840. And because our temperature is in Kelvin, down here would be in Kelvin. I now would like to show you another video of the practical application of Charles's law.
You know, Mr. Sams, I was at a triathlon. You know, I like to do those things.
Yes.
And at the triathlon, at the festival, they actually had hot air balloons.
Oh, that's fun.
And so I kind of showed a video of hot air. That's why we have the hot air balloons in our background picture here. And so, yeah, so let's watch the video of me at the triathlon. Here we have an amazing example of gas laws, Charles's law. What I've got is in front of me is a bunch of hot air balloons. In fact, one's way already up in the sky right here. And if you'll notice, occasionally what they're doing is they're throwing some fire. You can see the fire right there that they're throwing in. They're heating up some air. And as they heat up the air, what they're doing is they're causing the gas to expand, the air to expand. It is less dense when it is hot than when it is cold. Charles' law says is the higher the temperature, the higher the volume. It's a direct relationship, and by doing that, that of course allows these hot air balloons to rise up in the sky, as we can see with the one right here, who's way, way up there already. He's the first one to take off, and now the rest of these are about to take off in just a moment.
So now let's go on to our third gas law, and this is the last of the individual gas laws, and this is the Gay-Lussac's law. And in this law is our relationship between pressure, oops, got my ink again, pressure and temperature. And again, the temperature still, again, needs to be in Kelvin. Always, always, always in Kelvin. Okay, so now let's think about this as well. If the temperature goes up, that means the particles are moving faster. And if the particles are moving faster in a container, they're probably banging in, not probably, they are banging into the sides of the walls more often, first of all, and second of all, with more energy because they're going faster versus if somebody was banged into you slowly, it's not going to maybe bowl you over, but if somebody bangs into you quickly, they might knock you over. So in terms of pressure, as the temperature goes up, particles are moving faster, they are going to put more pressure on their container, and so the pressure goes up as well. And so again, the relationship here is direct, because as one goes up, the other goes up, or as one goes down, the other goes down. And again, it's going to have the same graphical representation, because as the temperature goes up, your pressure goes up as well. And so again, we're going to have the same basic mathematical equation as well, as P1 over T1 is equal to P2 over T2. It's a P, not a D. There you go. And so again, what I'm going to do is I'm just going to read off a problem. We're going to make a list, and then you're going to again plug and chug. It should be the same thing over and over again, just using a different formula. So here we go. The pressure on a gas changes from 20 kPa to 50 kPa. So the pressure 1 is 20 kPa, and pressure 2 is 50 kPa. When the temperature of the gas is changed to 30 degrees Celsius, so it's changed to 30 degrees Celsius, so that must be my second temperature, 30 degrees Celsius. If the volume was held constant, again, we have three variables, volume, temperature, and pressure. If I'm only talking about the relationship between temperature and pressure, my volume must stay constant. Otherwise, we're talking about a different law, because now we have three variables changing, but here we only have two. So it says, if the volume was held constant, calculate the initial temperature of the gas. So T1 is what I'm trying to find. Now again, our temperature, we have to make sure, my goodness, why does it not want me to do threes? My temperature has to be in Kelvin. All right. let's see, maybe I need to put it down here. So therefore, I need to add 273 to make it go to Kelvin. So now my temperature is 298 Kelvin. And so now that I have my P1, my P2, my T2, and so I have 3 out of the 4 variables, I can go ahead and do my mathematical equation and plug and chug. So please go ahead and do that. And then at the end, what I'm going to do is I'm just going to give you the answer this time. I'm not going to go through the entire algebra, and we can check to see if you have the correct answer. So if you went ahead and put in and you did the 20 divided by x is equal to 50 divided by 298, when you do the algebra, you should come up with an answer of 121 Kelvin. So now we're on to the last law, and actually this is the law that I think is of most importance because it's the combined gas law. It combines all 3 variables into one. So you can remember all 3 individual gas laws, Boyle's, Charles, Gay-Lussac's law, but in terms of formula, you really only need to remember one, which is the combined gas law, because if one is held constant, you can ignore that part of the equation. So let's go over that. So the combined gas law shows a relationship between all 3 factors, and the only constant is mass. The mathematical equation for the combined gas law, you're going to take Boyle's law, and you're going to combine that with Charles and the Gay-Lussac, where the temperature was on the bottom. And there's your mathematical equation for the combined gas law. So as you can see, if you remember this formula, if volume is constant, then you can just ignore the V and take the V's out of the equation, and you have P1 T1 equals P2 over T2. Same thing as if temperature was constant. You can ignore the bottom and just say P1 times V1 is equal to P2 times V2. So love the combined gas law because it makes things a lot simpler. Let's just do an example problem, and then we'll be done with the podcast. So let's see, sample problem. Hydrogen gas has a volume of 100 milliliters at STP. Ooh. So we've got volume 1 is 100 milliliters. It says STP, so I'm going to put down STP and come back to that because I'm going to see what it changed to know what pressure and temperature I'm going to be working with here. So if the temperature and pressure are changed to 0.5 atm, well, pressure is 0.5 atm because I know atmospheres is a pressure. So now I know down here my initial pressure has to be in atmospheres also, so that standard pressure in atmospheres is 1. And then it says it's changed to 0.5 atmospheres and 546 Kelvin. So the temperature is 546 Kelvin. And I technically didn't need to wait for temperature 1 because temperature is always in Kelvin when we're doing the gas laws, so 273 Kelvin. I'm assuming it's going to ask me what the volume 2 will be, but it says what will be the new volume of the gas. Yes, so V2 is what I'm trying to find out. So out of the 6 variables down here, I have 1, 2, 3, 4, 5 of them. I just plug and chug, put that in there, and solve for my x. So I'll set it up, and then I'm going to ask you to do the math, and then I'll give you the answer. If you are having a hard time with the actual calculation, the algebra about it, you can set it up, but then you get the wrong answer. That's when we have work time tomorrow, you need to come and see me, and I can help you out with that. Okay, so let's go ahead and plug this in. So we're going to take 1 times 100 all over 273 is equal to 0.5 times V2 all over 546. So I would take 546 times 100 times 1, and then I would divide it by 273 and divide it by 0.5 to figure out my volume. It's cross multiplying what I just did. So my V2 should end up being 400, and to figure out what my volume is, I look up my volume 1, and so it should be 400 milliliters. Okay, so tomorrow, the next couple days, we'll be doing some more application with this. Lots of word problems and practicing those word problems. We will have a CASEL learning assignment, as well as we'll do at least 2 labs with this application. So, here we go.